let's see how this works. So anyway, hello people. There's people here. That's amazing. Thanks so much for tuning in. Sorry. I guess I'll introduce myself, seeing as it's the first episode. So I'm Tom. I'm a researcher from South Australia. I'm technically doing a physics PhD, even though I did honours in chemistry, and I feel like I know way more about chemistry than I do physics. So my project's in it's really physical chemistry. It's like a spectroscopic detection of molecules. It's a sensing project, so laser applications. And all right. And then Oliver, do you want to introduce yourself as well?
Well, wait 1 second. My name's Oliver. I'm a Swiss student specializing in inorganic and theoretical chemistry. I'm the youngest one here.
But you also know way more about chemistry than I do. I feel like it.
Maybe in some fields.
Definitely in some fields.
Yeah.
Andrew?
Hi, I'm Andrew. Graduated from an undergraduate university in Michigan, and then also going to a PhD on the other side of Michigan. I specialize in mainly organometallic stuff, but I do like mixing into like PChem and spectroscopic stuff because that's fun.
Tariq?
Hey, I'm Tariq. I'm a fifth-year PhD student at Rutgers University in New Jersey. I work in mechanistic organometallic chemistry and catalyst design aimed toward controlled and selective functionalizations of simple hydrocarbon molecules.
And Claire?
Hey, I'm Claire. I did my undergraduate in Scotland at the University of St Andrews. Moved to Durham to do a PhD in organometallic chemistry, looking at group 9 complexes, so Cobalt mostly. And now I'm a postdoctoral researcher at the University of York, also in England, where I'm sticking with group 9 complexes, but looking more at materials applications now.
All right, thank you. So today's main theme is organometallic chemistry, as Tom probably mentioned it. And I think we should start by introducing the field, right, Tom?
Yeah, okay. So I feel like the only way to introduce a field these days is a dramatic reading of the Wikipedia page. And so I'll attempt to do the first screen sharing. Let's see how this goes. No technical issues at all. Here, and then here, and then here.
You're an optimist.
I'm a technological wizard.
Fire.
Yeah, we're going incognito here. All right, so we want Wikipedia. Yes, let's do this. Thank you. So what am I typing in? Organometallics? Will there be a Wikipedia page for organometallics?
There is an organometallic chemistry page.
Is it awful?
They usually... No,
oh, that's the journal. That's the journal. Okay.
Which
Organometallics.
Click on the blue link in the article.
Oh, yeah, that's the smart way of doing it. All right. Organometallic chemistry is the study of organometallic compounds. Okay. Well, that's not that helpful. Containing at least one chemical bond between a carbon atom or organomolecule and a metal. Okay. Sometimes broadened to include metalloids like boron, silicon, and tin as well. Okay. Is this correct so far? I suppose it's broad enough.
So far, so good.
Oh yeah, good. Okay. This is really quite big. Okay.
It's a decent. It's quite a good Wikipedia page.
It's just a lot of chemistry pages on Wikipedia are terrible. I mean, especially when they're trying to be entire fields.
Yeah, but I mean, organometallic chemistry is so popular. I guess they had to make it good.
Many complexes feature a coordination bond between metal and organic ligands. A naturally occurring thing is vitamin B12. All right, so it's you guys don't do any natural product stuff, right? It's all like
No one's doing bioinorganic.
Bioinorganic,
No.
yeah, that's a different field when it's like in enzymes or anything like that.
Yeah, metalloenzymes. I mean, they're cool, but bio stuff.
They're cool if they have cobalt.
Vitamin B12 does have cobalt.
Yeah,
has a
it does.
cobalt carbon.
There's a methyl on it. There's a methyl on the cobalt. Is there? I think.
In B12.
Yeah.
It's got so much stuff in it.
Yeah.
Yeah, it's a mess.
Oh, it's impressive. Oh, yeah, there is a methyl. Otherwise, it's just a porphyrin. Wait, it's not for me to talk. Wow, they want dimethyl cadmium.
As in other areas of chemistry, electron counting is useful for organizing electromagnetic. The 18 electron rule is helpful. Oh, sorry, this is flashing me back to undergrad. The 18 electron rule, like how early on in university did you learn that?
Chem 273, so it was like the sequence after general chemistry for my university.
Yeah, I think mine was like second year, maybe. I can't remember that.
We mentioned
So long
it
ago.
We mentioned it in the first semester, I think.
All right.
Well, you're
First, for the first. Come on.
Infamous, but yeah, for us, the 18 electron rule, counting, and really the deep dive into oxidation states and d-electron configurations came in our third year inorganic chemistry course.
Yeah. So it's something because if you do high school and that sort of stuff, high school chemistry, you don't come across organometallic chemistry just because there needs to be quite a lot of base knowledge in terms of like d-electrons, electron counting.
We don't cover the D-block chemistry in high school at all, which is super sad because it's the best part.
And I think at that point, they're really aiming to get you the rules of thumb. I mean, high school students are really learning the footwork and the concepts. Simple single bonds, Lewis dot structures. To really engage with the electrons, I think you need to have some understanding of molecular orbital theory.
Yep, 100%, especially for organometallics.
You could introduce the basics of MO theory, though. To some point.
In high school?
Yeah, I think so.
That's a little early.
I think high school students are smart enough to do that if they're specializing in chemistry.
We did a little bit of transition metal chemistry in high school, but it was basically just looking at ligands coordinating. So we looked at like bidentate, tridentate ligands.
We didn't even do that.
It's super basic.
See, my dad's an inorganic chemist, so I've kind of been around it my entire life.
What I've learned about high school students, though, is that you can basically teach them anything you want to teach them, so long as you don't tell them what the name of the thing you're teaching them is. For example, we've had some really talented high school students in our lab. One of them I can think of, I was, his first week in the lab, I was just casually explaining to him how to interpret NMR spectra. And, he was perfectly grasping it until someone walked in and said, you wouldn't normally learn that till your third year in college, right? Like, no. We can't put up those barriers in their heads now. You just have to launder this knowledge into their heads.
I know high school students who can do their better retrosynthesis than I can. So those are exceptions, I suppose.
And you are in Europe, so it is Europe high school. I feel it's sometimes a bit more advanced than Australian high school.
Better than the US or Australia, yeah.
All right, well, this is probably enough.
Organometallic chemistry.
All right, we're experts now. We've perused the Wikipedia page. We're now all experts.
What about the applications? What's it good for?
Well, yeah, true. History, sure. Skip that section. Catalysis, so commonly using catalysis. Is that what most, because I feel like that's what most people in the field kind of aim towards, right? It's all like a catalysis.
That's exactly how I say as well. It really overlaps with catalyst design and mechanistic understandings of catalysis.
I mean, everyone's
like-
doing catalyst design nowadays. Like
My project
basically
wasn't
all
explicitly about catalysts, but it could be applied to a catalytic situation eventually.
Andrew, aren't you doing one in the high oxidation state nickel chemistry during your PhD?
Potentially, I just have to choose an advisor first.
Yeah.
Oh, someone did organometallics in high school.
Oh,
That's actually
it's
interesting.
too advanced.
Where were they?
I mean, sure, we mentioned Grignard reagents, and organocadmium for some reason. We mentioned making ketones with organocadmium in high school, and I don't know why.
We mentioned olefin metathesis. I went to high school way long ago, and that was the Nobel Prize was still pretty recent then for Schrock and Grubbs and Chauvin.
Guys, there's a question about ferrocene. Has anyone done stuff with ferrocene derivatives? And Andrew, of course.
Iron cyclopentadienyl bicarbonyl 2. So it's the fifth cation, and my research revolved around coordinating an alkene of that.
Well, I think people get the idea. We need carbon metal bonds. We use them in catalysis, and we get some organometallic molecules, which are important in biology too. But they're mostly important for catalysis, and also ferrocene is used in fuel, isn't it? You made a video about that.
Yeah, sometimes it ends up as an anti-bumping stuff in fuel. So they put it in there.
And there's a carbonyl manganese complex as well.
Yeah, it's a piano stool manganese compound.
But I mean, besides catalysis, there are certainly other applications of organometallics, and sometimes we often forget them while we're mesmerized by the cool catalytic applications. But there are actually medicinal compounds, bioactive organometallic compounds.
Usually isn't.
Cisplatins is a famous example. But anti-cancer drugs based off of organometallics is a continuing field.
Well, standard cisplatin isn't, though, because it's just ammonia coordinated to it, right?
2 ammonias, 2 chlorines.
Yep.
But also, I believe in molecular electronics as well. I remember I read something recently about a ferrocene polymer.
What?
Yeah.
I could imagine that sort of.
Yeah, I mean, you can make a mega sandwich with it.
All right, sorry. Let's jump to a presentation now that we're experts. Really keen to see some of your work. So I think, Claire, you're going first.
Yeah, I can do.
Right.
The one thing I want to say before we start, I don't have any carbon metal bonds.
All right, okay.
I'm not talking about I'm not talking about the catalysis. I thought I'd keep it really simple and show you one reaction and the different ways it can go.
That's great.
So forgive me, but
that's fine. No, that's
perfect.
Okay, hold on. I'll just share this with you. You see that?
Yeah.
Flash. Okay. So I'm going to talk a little bit about a very small thing that I did during my PhD at Durham University. So I was supervised by Dr. Phil Dyer, who works there. And this is a bit about the reduction chemistry of cobalt diphosphine complexes. So so the main aim of my PhD was to design and develop a homogeneous cobalt-based system for regio and stereoselective linear alpha olefins. That's a terminal alkene to LAO oligomerization reaction. So we're looking at cobalt diphosphine complexes for this. So diphosphines in particular, these ligands, we thought were going to be really useful. So they're highly tunable, so you can change the substituents both on the phosphine and on the backbone. So that's going to help gain some control over the metal center's reactivity. And a diphosphine as well. These are going to be less labile than, for instance, the monophosphine. So they should hopefully stabilize any low coordinate complexes that we might form during the catalytic cycle. And then as well, cobalt diphosphanes, in the last couple of years especially, have been shown to be active towards olefins in a variety of reactions, right? So synthetically for me, I was looking at making cobalt-1 complexes, which is quite a rare oxidation state of cobalt, and then ultimately asking, can we use them in selective LEO to LEO dimerization reactions or oligomerization? So to make cobalt-1 complexes, this is where it gets a bit trickier because they are so unstable. So to start off, I was actually looking at making some cobalt-2 complexes. So these are really easy to make. So this is all done air sensitively, so using the Schlenk line. So starting from a cobalt-2 halide, mixing it with a diphosphine ligands, and then you get a cobalt diphosphine dihalide. This goes in pretty much quantitative yield. And then in theory, what you should be able to do is just add a reducing agent like zinc to do a single electron reduction and get a cobalt-1 complex out. So I made a whole load of cobalt-2 complexes, and they all react a little bit differently. Just to give you an idea, I'm just going to compare 4 of them today. So complexes 1 and 2 have both got phenyl substituents on the phosphine ligand. And complexes 3 and 4 have both got tert-butyls. And as you can probably guess, they react a little bit differently towards zinc. So complexes 1 and 2, when we do that reduction, it goes as we'd expect. So we do a single electron reduction to cobalt-1, forming a dimeric structure. These actually bridge through 2 halides. And we can follow that by Raman spectroscopy. So Raman's really useful. So in the cobalt-2 complex, our starting material, we have this symmetric stretch in the Raman. And then when we reduce them, we take one of those halides away. So we lose that band. That's a really good spectroscopic tool for probing these complexes. It's really easy to do air sensitively as well. And then we can also follow these by UV vis or some inert mass spectrometric technique as well. But for our tert-butyl substituted diphosphines, these reacted a little bit differently with zinc. So actually what we saw forming was a zinc-2 diphosphine species, which is quite unexpected. So we're making zinc-2 bromide in the reaction, and then it's starting to pick up our phosphorus ligand. So in the UV vis, we're starting from this blue line. Over time, we see reduction in our cobalt-2 complex, and we start to produce cobalt bromide as a side product, as our diphosphine ligands picked off by the zinc-2 halide that we're producing. And we can follow that again by Raman, single crystal X-ray diffraction if we crystallize the product mixture, phosphorus NMR because the zinc complex at the end is diamagnetic, and our inert atmosphere mass spec as well. So what's going on? Why do these react differently? So we looked at the structures of these complexes. So these are single crystal X-ray structures of the complexes, and we can start to look at the parameters that you get out. So as you'd expect, moving from the phenyl substituted diphosphines 1 and 2 to our tert-butyl 1, we're making this ligand much more bulky. Our percentage buried volume goes up. So that's just an indication as to how congested the metal center is around. But what was quite interesting was this halide-cobalt halide bond angle in the solid state structure. So in complexes 1 and 2, this was really wide, so about 120 degrees. So that's really quite a significantly distorted complex at this point, because you would expect this to be sort of tetrahedral. Mm-hmm. And we can see that in that tau4 parameter. So tau4 is a 4-coordinate geometry index. When it has a value of 1, it means it's perfectly tetrahedral. When it has a value of 0.85, we're actually trigonal pyramidal in geometry, and then 0 is down to square planar. So we're actually starting to approach trigonal pyramidal geometry in these complexes 1 and 2. And we think this is key to getting a successful reduction of these complexes. So when we've got this distorted geometry, this allows us to stabilize this sort of dimeric cobalt species which we're forming. Whereas our more tetrahedral complexes, these tert-butyl ones, these can't form a stable cobalt-1, and instead, through a disproportionation reaction, we're producing metallic cobalt, cobalt-0. So that's really easy to spot because it'll actually stick to the stirrer bar in the reaction. You just pull it back out again. Then we're producing free diphosphine ligands, which can then get picked up by our zinc-2 halide, which is produced as a side product of that initial reaction, of that reduction, to form our zinc-2 species. So I thought this was quite a nice example to show you guys of what quite a small change in the distortion of the geometry of a complex can have such a big impact on the reactivity. And I think this is going to be really important in catalysis, because a lot of people use these sorts of things in situ for doing a variety of reactions. So that sort of brings me to the end, I guess. I want to thank all the people on the slide that nobody watching this will have a clue who they are. There's some pictures of me during my PhD, and you guys, of course, for inviting me to chat today.
Well, you're welcome. It looks really interesting. There's only one like semi-stable cobalt complex, which Cobalt 1 complex, which is as a triphenyl phosphine chloride one, I think.
Yeah. Mm-hmm.
The only time I saw Cobalt 1.
That one I think is actually air stable.
It is. Well, for some time, I remember I made it in air, so I think it's stable enough for that. But I imagine yours aren't.
Yes, I've made that quite a few times as well. That's a really nice complex, and that's I did try using that to try and get into some of these Cobalt 1 complexes. So doing like a ligand exchange reaction, just knocking off some triphenylphosphine and sticking on a diphosphine instead. But sadly, those ones also disproportionated. So it really is a ligand effect that we're seeing here.
Someone's asking if you're only focusing on cobalt.
During my PhD, yeah. Now I work with a few other elements, but my PhD I looked at cobalt diphosphines, cobalt diimines, and some cobalt cyclopentadiene complexes as well.
Oh, well, awesome. The cobalt one is so cool.
Cobalt it's very tricky to handle and put up with. It's paramagnetic, so you can't NMR it sort of at all. But once you get a handle on it, it's like I think it's quite rewarding because I mean it's really cheap for applications. It's really
unlike iridium, for example.
Yeah, exactly. No offense.
Or rhodium is horrible as well. I mean,
rhodium's so expensive.
Iridium is less expensive than palladium these days. So I'm just going to put that out there.
You know what's even more cheap? Iron.
Someone's asking what makes cobalt interesting.
What makes it interesting? Cobalt has this, so the 3D metals are, I think, particularly interesting transition metals because they have access to loads of different spin states, and as well because they're so small, they can react to ligands in a way that some of the larger D-block elements can't. And I think I sort of started to touch upon that in my presentation. So the cobalt has this sort of uncanny ability to be able to change geometries to sort of fit any ligand that it wants, which a lot of other elements just wouldn't do.
Someone else is asking about the characterization of the complexes.
Yeah, so characterizing cobalt complexes is quite tricky. So all of this was done air sensitively, first of all. So I think I've got some cheeky extra slides. I've put some pictures in.
Ooh.
So first of all, the top one is a Schlenk line. So this is where I do all of my work. Well, this is where I did all my work in my PhD. Please excuse the mess. This was a before and after photo. So for instance, air sensitive UV vis. So usually for UV vis, you just use a cuvette. So what we have here is a quartz cuvette that then has a quartz to glass adapter and then a little tiny Young's tap on it. So that means that I can put the quartz cuvette on my Schlenk line or take it into a glove box to prep the samples. The bottom left picture is a picture of me doing some Raman spectroscopy. So this is just a J. Young's NMR tube. So it's an air-sensitive NMR tube, a little bit of solid in the bottom of it. And then I can just shoot it with a laser to do the Raman spectroscopy in the atmosphere. All the reactions are done in Schlenks. I've got a little picture of an NMR. So I can't remember which complex that was. I think it's a cobalt cyclopentadiene complex. It might be. Really, I've got no idea. I mean, it's a blob. You can't really NMR cobalt, really. And then the crystallography you can do air sensitively as well. If you put them in oil under a stream of nitrogen, or if you pick them in a glove box.
Those crystals are beautiful.
Aren't they? They're so nice.
Hey, there's lots of questions streaming in, but I reckon we should press on to another presentation, if that's okay.
Yeah, no,
I'll just point out that the cleanest hood is the one that does no work.
yeah.
You should be dirty.
This was after I think, after a really, really busy week where I was just trying to drastically get loads and loads of data so I could go home and write my thesis. I was like just throwing stuff anywhere, you know.
People watching my videos are so desensitized to what a messy lab is at this point. I think I could just do a reaction in the middle of a field and people would...
Buckets in a shed.
Yeah. People let me get away with it somehow.
So, Andrew next?
Sure.
Yeah.
It's actually a pretty
Thank
good
you,
transition
Claire.
into mine then.
Yeah, thanks.
Yeah, no worries.
Amazing chemistry.
All right, so share screen. All right, so here we go. This is some of the research that I did in my undergraduate studies. I did it over the course of about 2.5 years, but I didn't start on this specific portion of it until like a year in. It's a series of some N-methylaniline substituted iron alkene complexes, but we have to first discuss how irons actually coordinate to alkenes. And that's through the Dewar Duncanson model. So we have a full pi orbital on an alkene, which is the pi cloud that we usually know from organic chemistry, interacting with an empty d orbital on the metal center. Specifically, in my case, it's going to be iron. But there's also a second interaction where an unfilled pi star orbital, its antibonding orbital, is back-bonded into by a full metal d orbital. Now, there's very extensive pi donation and pi back, sigma donation and pi back bonding depending on the electron density of the metal. So if we have an electron poor metal, the metal drains electron density out of the alkene, and this can activate the alkene to nucleophilic attack. But if we have an electron-rich metal, it turns into a metallocyclopropane, which is an electron-rich metal and can also be used as a protecting group. But specifically, there can be distortions to this. So the alkene can rotate around the metal bond axis. It can shift around like a barrel, like on the outside of a barrel. C, it can slide, the metal can slide along the face of the alkene. And in D, it can tilt towards and away the metal center. Specifically, my complexes follow always distortion C. And we can get this value from X-ray crystallography using the two bond distances from the alpha carbon here and the beta carbon here, taking the absolute value, and we get what we call the delta parameter. So in a symmetric iron alkene complex, the delta is 0 angstroms. And then as it slides further over, according to distortion C, we get a higher and higher amount of delta. But as Claire also said, distortion has a massive effect on reactivity. And these delta values must be obtained from crystal structures. So as I said earlier, I work with FIP cation, and here are 3 complexes that were studied previously. We have iron with alkene, one that's substituted with a methoxy group, and one that's substituted with a dimethylamine. Now, these have varying amounts of distortion. The lone pair on the oxygen, or any heteroatom, pushes the iron center over just a hair, 0.23 angstroms. And if you change it to a nitrogen, nitrogen has a better energy match for the developing unfilled orbital here. So we get a stronger interaction and more distortion. Comparing the rates of nucleophilic attack at this specific carbon, we can set the relative reactivity of this one to 1, and then compare the others to it. So for the methoxy derivative, it's 530 times more reactive, which is a large increase. But if you push the iron over further, you expect, okay, some is good, more is better. But it turns out it's totally inert. They left the flask on the table for 3 days, and there was still no appreciable rate of reaction, according to NMR. So we posit that the author of that study, Rosenblum, didn't find the top of the surface, that the methoxy substituted alkene was not the most reactive one that he could make. There's some other point that this could be on either side of. So my task in this research was to find out what could lie at the top of the reactivity surface, but also to create a series of compounds that systematically changes the position of the iron. So we can figure out how far it is through single crystal X-ray diffraction. Here's some of my crystals over here. Let's skip through this. And here's some of the crystals that I made. We have the methoxy substituted one here, but specifically it's N-methyl aniline substituted. So by swapping off one of the methyls from the dimethylamine derivative to an aniline ring, along with changing the X position, the para position, we can have fine-tuned control over where the iron is located, and we can get these displacements. The para-acetyl structure was absolute garbage, by the way. And as we decrease electron donation properties, we can see that the displacement goes down as we shift from electron donating in the paramethoxy to electron withdrawing in the paranitro. It's allowing less of the lone pair on the nitrogen to donate into the alkene to push the iron over. Yeah, that's it. We should have reactivity data, but it's quite a challenge to get air-sensitive kinetics done at an undergraduate university.
Oh, they're beautiful, though.
Yeah.
What are you going to do now?
I still haven't decided on an advisor, but for my PhD, I'm either going to do nickel or some other first-row transition metal because those are the most relevant ones right now because they're both cheap, abundant, and can also be fine-tuned to do a lot of the catalysis that heavier metals like palladium, platinum, and iridium can do.
Yeah, I mean, iron's the holy grail of catalysis, really.
Mm-hmm. I mean, this is a stoichiometric system, but by using an iron in a different system and sterically forcing the alkene to distort, we can potentially increase reactivity that way.
People want to see the crystals again, the nice crystals.
Okay.
Are they all orange?
Yep, they're all just a various state of orange and yellow.
Oh, no.
Interestingly enough, if we swap the N-methyl to
yellow,
yes, yellow. This is why it doesn't work. Okay, so we were trying to create phenoxy derivatives because the OMe derivative was higher than the N-dimethylamine. So if we swap off the methyl to a phenoxy, we should see even more reactivity. But they're all yellow. They don't work. I spent like half a year trying to make these goddamn things. And I couldn't because they're yellow.
Okay, some questions. Someone's asking, what can it be applied for?
It's really just basic research. It's an interesting question to see, okay, why is reactivity just switching off as soon as we distort too far? What is it about the system that's causing that? Really, there's only applicable stuff to catalysis. So, like, say, with a Ziegler-Natta polymerization, I actually have something on this. So, the intramolecular chain growth step here is part of the Ziegler-Natta catalysis. So, if we can distort this complex just a hair, then we might be able to increase reactivity even further. But that would mean using a different metal, probably. Namely, zirconium and titanium,
Or
and
usually,
I believe hafnium are used for Ziegler-Natta.
everyone's saying that yellow chem is trash. Like
Yeah.
funny people.
It's trash. It's
I
total
disagree.
garbage.
Not yellow isn't always trash. Some complexes are just inherently yellow. You have to look at the crystal field splitting parameter. It's like,
Yeah.
Yellow never works, ever. It's trash.
Okay, any more questions, guys?
So
okay, there's
I have a question from chat. It says, was it difficult for you to grow large enough crystals for diffraction here,
Yes.
Tariq's?
It was a bitch and a half. Okay, so my
What's
unit
that in
have
actual
a
unit?
fridge in our glove box. So I would have to assemble the recrystallization in a Schlenk line by layering in a Schlenk bomb and then carry it without disturbing it into the minus 20 degrees C fridge. And it took about 10 attempts to get the crystal structure of the paraacetyl. I have the paracyanyl one too, but that one only worked because my dad, who was a crystallographer, his university got another X-ray machine that could process even smaller crystals. So like some of the smallest ones there would be suitable on it, whereas you would have needed something like that size. That's the only reason why I was able to get some of these crystals.
Yeah, sounds like great.
Yeah, it's a total nightmare because it was layered in air-free, degassed and dry ether, DCM, and then a large ether layer, and getting the ratios right to get these to crystallize out was a nightmare.
I go to DCM hexane or DCM pentane.
We didn't have hexanes or pentanes available.
What?
Ah.
That's crazy.
I would
that
have
would
to
have
dry
worked
it
so much better than ether. Let me just tell you.
Yeah, probably. I would just have to have dried it myself. And DCM ether worked for a previous batch of crystals. So
Yeah,
one's with an H with an aniline instead of an N-methylaniline. And there's actually a paper on that I can link in chat.
It's Tariq's turn now.
Yeah, let's go to Tariq. Yeah.
All right.
Thanks for being patient. Mate.
Thanks, Andrew, by the way.
Oh, of course. Yeah, no, great presentation. Of course.
Share a screen, then let's see what we got here.
Everyone's thanking you, Andrew, and everyone's thanking Claire, by the way.
All right, so I'm gonna go probably an inch deep and a mile wide with this presentation, not talking about the broader field I'm working in and the research topic rather than my specific PhD work. So I'm going to give you a short story in CH activation, namely the selective conversion of alkanes to alkenes using iridium pincer complexes. So to begin and to give you an appreciation of this wider, very hot topic, transformative topic in organic chemistry and organometallic chemistry, which is CH activation, it's a strategy that enables us, in principle, to arbitrarily functionalize the ubiquitous CH bonds of organic molecules. And this has applications in fine chemistry. Where's my pointer? 1 second. There we are. For example, we can just take this bond here, the CH bond on the indole ring, and just add it or form a new bond to this alkene, and enabling a blazing fast synthesis of a complex molecule. But it also has applications to commodity scale chemistry, such as methane functionalization, partial oxidation of methane to methanol. And there are a couple different strategies and variations on this theme of how metals insert into CH bonds. I won't talk about all of them in detail. Some of them they all have their scopes and limitations and particular strengths. But the one I am going to talk about is simple oxidative addition. This is the one that's taught in introductory or the intro chapters of organometallic chemistry books. It's a fundamental reaction of organometallic molecules. So low valence, late transition metals, fourth and fifth row, can insert themselves into an alkane CH bond. And then when they do that, 1 second, sorry, too far. A common downstream reaction or subsequent reaction is beta hydride elimination. And this generates an olefin and a new metal hydride bond. So when you look at what's happened here, in a stoichiometric sense, we've taken an alkane and turned it into an alkene. Now, wouldn't it be cool if we can turn this iridium dihydride back into this 3-coordinate iridium? Well, it turns out we can. If we just heat the crap out of this, up to 200 C or so, it'll off-gas H2. This is an endothermic process, and we call this acceptorless dehydrogenation. A more mild approach is to hydrogenate a sacrificial olefin and produce an alkane, thereby basically redistributing the double bonds in a catalytic pot. And we call this transfer dehydrogenation. And this is an enabling strategy. I don't have to tell you how valuable olefins are as intermediates in industrial organic chemistry and even fine organic chemistry. I mean, they're used in pericyclic reactions, olefin metathesis, oligomerizations, what else? Borylations, silylations. They're all over the place. But some real magic can happen when we combine this with the second catalyst in a downstream reaction. We call this alkene metathesis. It's the net disproportionation of alkane chain lengths. So we start with like a hexane, and with one cycle of alkene metathesis, we get decane. Now, we can do this further and get higher hydrocarbons and also some lighter ones. But what this range here represents is transportation range fuels. We've taken something that has little value in fuels and turned it into something that's much more commercially viable. Another approach is going the other direction, taking very long hydrocarbons such as polyethylene and plastic bottles, plastic waste, and mixing them with hexane and a little bit of catalyst. And guess what? Diesel comes out the other end, clean diesel. So this kind of demonstrates the power of being able to do this new fundamental reaction on alkanes in a controlled sense. And now it's no accident I showed you the pincer complex at the 2 slides ago. Pincer iridium complexes have been the flag bearer, the standard bearer for this type of reaction, for alkane dehydrogenation. And over the years, we've organometallic chemists, we are tinkerers. We like to build little molecular robots, if you will. That's what catalysts are. That's how I think of them. And so we've explored quite a bit of chemical space in terms of the ligand design, and each has its merits. Each has its own motivation behind it, whether it was just random exploration or computation-driven or mechanistic insight that led to some changes. But the field continues to grow. Even yesterday, this family of catalysts was reported from the Zheng Huang group at Shanghai Institute of Organic Chemistry. And kind of illustrate the kind of people who go into organometallics. We are Lego people. We like to build little toys. This is my coworker's old Connect Ferris wheel, and it's become the most noble and great NMR spinner in this country, possibly the world. I guarantee you this is the best one out there. It spins 12 NMR tubes at a time. Can't beat that. So now I'll tell you a little bit about my research, which is on hydride oxidation. So it's well and good to be able to simply extrude hydrogen. In fact, that's very commercially desirable. But using sacrificial olefins is not so desirable. What we really want to do is to use things that are abundant or recyclable, at least. Things like oxygen from the air, or benzoquinone, which we can easily filter off and regenerate with oxygen from the air. Or better yet, what if we could use this in an electrochemical cell and harvest the electrons that come off and to do electrical work? This has potential, I think, pun intended. Another approach, given that we are working with iridium and we are talking about commodity scale applications, we want these catalysts to be recoverable. So in this field, as well as many others, there's this interest in tethering homogeneous catalysts onto heterogeneous insoluble supports, thereby creating a single site catalyst. One example of this, using a pincer iridium catalyst, but for CO2 reduction, where they take this pyrene tag and append it, or just basically stick it onto a carbon nanotube by the strength of its van der Waals interactions. And what this enables is, for one, facile recovery, 2, it sequesters incompatible catalysts and perhaps a tandem catalytic mixture. It also improves the stability of the catalyst by inhibiting bimolecular decompositions. And often, or at least sometimes, we've seen it improves the thermal stability of the catalyst. What I think the real direction and forward direction is, as much as I love iridium, I think iridium is the coolest metal in the world. But
and the most expensive one.
Palladium's more expensive, and so is gold, at least these days. But right, there is certainly some pricing volatility in it. These are the platinum group elements in general are not earth abundant. They are rare. They have competing applications. And ultimately, if we're going to talk about large-scale transformative chemistry that's going to change the metabolism of refining and our energy systems, we want to be able to do it with base metals. This is a very vibrant area of research, as we've seen already. But it's also not out of reach for alkane dehydrogenation either. The irony of this report, besides that this complex is made out of iron, is that this was reported in 1987. So this research is cyclical in terms of the base metals versus precious metals. I guarantee you in like 20 years, people will be looking at iridium and palladium again. But I think there's it also says a lot that we often find inspiration for new research directions by looking at very old research directions with new eyes. So that's all I really have for you. And so I'll just acknowledge my group and the people who've allowed me to do or gain this level of appreciation of the field, the funding agencies, BASF, and also I have to credit some early inspiration from the Science Madness discussion board for really, instilling in me this interest in chemistry.
Always Science Madness.
Of course, yeah. One of the original members.
Yeah. Original members, yeah, I know. It's an old forum, I gotta say.
They're asking about the future of green chemistry. Why?
Green chemistry.
What activation, I guess. And
I mean,
yeah,
organometallic is basically a green field. I mean, we don't use green practices, but it's always for catalysis usually.
I mean,
catalysis is one of the principles of green chemistry, right?
Yeah, well, I think it is like
air stable and do it in green solvents, then it's a winner.
Perfect, isn't it?
Well, the idea of using oxygen as a terminal hydrogen acceptor is very much in line with green chemistry.
And use safe reagents like 5 grams of osmium tetroxide.
Oh yeah, metal oxides, But I think what it's come down to is everyone's become a green chemist. I don't know if there's a discrete field that's really green chemistry. Green chemistry is this aspirational goal that I think we're all kind of working toward in some form or the other.
Someone's talking about carbon monoxide.
As far as the research affected by the global health situation, almost all university research labs have been shut down. Like if you're not working on COVID-19, you're not in the lab.
Well, I just grabbed these gloves from the lab. Sorry to anyone who's watching, but yes, our research is shut down. Our operations are also shut down.
Well, how can you apply organometallic chemistry to biology?
Biology.
We'll dehydrate the crap out of it. I don't know.
All right. Thank you, Tariq.
Thank you. Does the price of the metals affect your research at all? Because I know someone was doing, when I was doing honours, they were doing ruthenium chemistry when it did that huge skyrocket in price, like back a couple of years ago.
There's certainly some volatility in the prices of these things, but to be honest, it doesn't affect us that much. And I mean, people don't believe when I say this. These things aren't that expensive. When I show you like some of the catalysts I work on and have built, the most expensive part of them is actually the ligand, not the metal.
That's quite often the case, yeah.
I mean, even if you order like standard ligands like DPP, they're like more than $100 for a gram. So
also we've early on, I think our lab benefited from just a donation of rather large amount of iridium trichloride or iridium codchloride from Johnson Matthey. And over the times we really do kind of like keep an eye on the precious metals market, and when it's low, we buy it in bulk.
Right now is the time to buy rhodium, iridium. The price has been crashing the last month, so
all right.
To buy everyone.
All right, there you go. Now we're in business. But what it often means, though, it's kind of a quirk in that the precursor you have access to is the one that's the cheapest at the time. So sometimes you have a lot of like hexachlorouric acid or the potassium salt of that. Yeah, and it might not be the most convenient one to work with to build the other metal sources, but it's the one that we have on hand, so we have to learn to work with it.
I mean, don't universities have a huge stash of platinum group metals because they were super cheap like 20 years ago?
We certainly have some leftover stuff from labs we've inherited. We actually have a fair bit of like platinum salts, but we don't do platinum chemistry, so okay.
I've seen some platinum salts from the 70s in an ampoule. So.
Yeah. A question for everyone: what's the sort of scale that you work on? Because I suppose we're talking about price, but is it all very small?
For me, it was all like about 250 milligram scale. So enough for an NMR tube reaction, enough to try and get a crystal, enough for an IR. That's it. For
me, when I do my preparations of my complexes, I'm using about 90 milligrams of the iridium salt. It's iridium cod chloride dimer. And then when I'm doing the characterizations, each NMR scale reaction, I prepare to about 10 millimolar concentration. So that uses about 3 milligrams of catalyst and or 3 of complex. For catalytic reactions, about the same, 3 milligrams or so. So when I make a batch, which actually works out with that 90 milligrams of cog fluoride, it comes out to about 150 milligrams of catalyst. That's 150 milligrams lasts quite a while.
For me, it depends on the metal. It depends on the reaction. If I make some of my cobalt work, I did gram scale. Yeah. I was like, well, we had like some of them. So some of the ligands, even though they're really expensive ligands, sometimes you just have a massive pot of it. So you think, I'll just make 5 grams of this complex.
Oh, God.
Well, then you don't have to make it ever again.
Yeah, but you need a huge slag tube then.
Yeah, we got big slag tubes. It's fine. The solvent's more tricky. But then, yeah, so I've started more recently. I've been doing a lot of iridium work, and that I definitely do on a smaller scale.
Iridium.
Yeah.
A lot of like the main compounds that I made were about 250 milligrams, but the precursor ones we wanted to do in batch work. So I would routinely make like 5 grams of K-FIP, which is a little bit of a difficult synthesis.
What is the biggest scale reaction you've done?
5 gram.
With a metal?
Yep.
Any?
Case electride plus FIP dimer. You can break it apart, just reflux it for about 3 hours, and you get really nice, clean K-FIP, which you can use for a nucleophilic attack.
I think
a lot better than using sodium mercury amalgam.
Everything's better.
I think I've only really worked in this lab on like a 500 milliliter scale or so, and as far as like products, I've made like 20 grams at the time of my precursor for my ligand. And that's really easy. It's a simple condensation. It's the Hansch dihydropyridine synthesis. You just mix these things and it crashes out like yellow solids. You filter them off, wash them, done. It's feel-good chemistry. But I think the most interesting one was that 500 milliliters of super deuteride I was making, which is a very viscous, intensely pyrophoric solution that had to be cannula filtered.
Lovely.
Oh, God. You, Claire, what's your largest scale?
Is that, again, ligand precursor prep, precursor to precursor to precursor. So it's making diphenylphosphine from triphenylphosphine. So just ripping off a phenyl group. Start with 50 grams, and then you just throw loads of lithium in it, reflux it, and then distill out the diphenylphosphine at the end. Which is fine, except from what I didn't realize the first time I made it is the diphenylphosphine leaches grease. So the joints on my distillation setup are seized. And that was fine. I dealt with it. So I cannulaed out the diphenylphosphine, got it nice in an ampule. But what I forgot was on my Schlenk line, I have a mercury pressure gauge on my vac line. So I forgot that. The next day I came in and tried to test the pressure and just snapped it. So my vacuum was on, so I was sucking air into my trap, and then there was mercury in glass.
Oh, that's horrendous.
Oil bubblers, that's the way to go.
Oil bubblers.
I didn't break my bubbler, it was just the pressure gauge. But
that same sort of mercury backup happened to me once. It was really embarrassing because I was training a new graduate student. And, it's supposed to be this experienced graduate student. Here it is. I filled up my Schlenk line and my reaction with mercury and had to spend 3 hours just assembling it, cleaning it out. So
it's the worst.
Yeah.
You get the best pressure with a mercury line.
Yeah. So most lines you still use the mercury, like a big pot of mercury, and your air goes through that because the mercury is really a liquid but really heavy, right? So it can keep the pressure well. Is that the idea? Yeah.
Yeah, and there's absolutely no chance of any setback of oxygen as well.
Yeah, so that's surprising to me to see, there's always these big mercury bubblers, and people have accidents with them all the time. It's really easy to get mercury everywhere, but everyone does it. What can you do?
I think once they're there, it's
surprisingly
more hassle
common
to get rid of them.
Mercury is easy enough to deal with when it's metallic.
Yeah, elemental, yeah.
I mean, you can. Well, since aqueous mercury is fine too, you're just so fine.
Sure.
Tom.
Big question for me is, what do you think of the field? Because at some point in undergrad, like you have to decide, hey, I'm going to do organometallics, rather than any other field. And do you feel like you've made a good choice? And like, if you were to sell this field to other people, what do you think are the best things you get out of it, sort of thing? I know that's like 8 questions in one, but
I can mind if I jump in on that?
Yeah, go.
Sure. Absolutely, I think I made the right choice. I haven't looked back, and hell yeah, I'd do it again too if I had the chance to do it again. The thing I like about organometallic chemistry is that it's kind of a small field. It's like a subset of organic chemistry, perhaps, which means everyone knows each other on a first-name basis, and they all have to kind of play nice together. Everyone's very friendly, at least that I've met. And so the organometallics community fills up maybe like 2 conference rooms at an ACS meeting. I've had the chance to meet several of my heroes, people like, I was a big fan of Maurice Brookhart before I started graduate school. I was also working in synthetic catalysis. So he's my hero. I got to meet him several times. He's great. I got to meet John Hartwig, who wrote the book on organometallic chemistry. I don't know. I love it.
So is it not too small? Do you ever feel like the field is too small, or is it a nice sort of thing?
Yeah, you can do so much.
There is a lot of breadth in what you can do with organometallics, but it's very specialized. So you have to know all about inorganic chemistry, organic chemistry, physical chemistry, and it all comes together for organometallics. So you have to be really well versed in all of those 3 in order to actually make any significant progress. That's what I find interesting about it, but it is definitely a turnoff for a lot of people because it's just so multidisciplinary.
I think the further you get into any subset of research, though, in chemistry, you have to end up knowing so much about all the different aspects of chemistry. So I think it's actually a bit of a problem in the way it's taught, and it's taught in this sort of pillar system where the fields are really separate, when actually in research, you have to be able to apply concepts from all of them.
Right.
And in my mind, in terms of gaining employment, going into industry after a PhD, do you feel like the organometallic sort of area lends you well? Because I feel like in my mind you're doing like a lot of characterization techniques, and you're also doing you're doing your organo, and you're also doing your inorganic. So you can kind of go into quite a different fields. Is that correct, or do you...
It depends.
Yeah.
I think anyone considering graduate research needs to go in with open eyes and bear in mind that the job market is very competitive.
Yeah.
It doesn't matter which field you're going into. It's not just academia. It's equally so, maybe more so for industry. So I actually had the chance to talk to someone about this recently. A scientist at Merck who I ran into at the conference, and what she had told me was that organometallic chemists, particularly mechanistic organometallic chemists, often face some skepticism when they try to go into things like medicinal chemistry or process chemistry. The feeling is that they don't have enough of that organic chemistry background. The real strategically inclined synthetic planning type mentality. So that's easily remediated by just choosing a postdoc that will train you in that. So long as you're bringing something to the table for your future postdoc advisor.
Claire, how do you feel about the field?
Well, I'm not actively trying to get into industry at the moment.
Did you consider it, or was it always looking at doing academia?
I've always sort of been looking at doing academia. My PhD was industrially sponsored though, which is quite unusual for a homogeneous catalysis project, especially. So I would say if you're doing organometallics and you're doing it homogeneously or any sort of catalysis like that, then that's not how they do it in the industry. Everyone uses heterogeneous. They try and make it cheap and cheerful, and they want it to stick in that reactor for 30 years and never have to change it, which you can't do with a homogeneous catalyst.
Well, counterpoint.
Yeah, go on.
The Walker process, Monsanto acetic acid process, hydroformylation.
Yeah, but Like, I think it's about 95% of industrial processes that run catalysts are running them solid state.
True.
Yeah. There are exceptions, of course. But then it's, I mean, a PhD is not just about learning chemistry, is it? It's problem solving, and it's all the soft skills that you get at the same time that you don't even realize that you're doing. And that's what you should be selling yourself on in an industrial perspective. That's what they want, I would say.
There's a question about computational work. Is anyone doing any?
Yeah.
It's usually pretty required for most high-level journals now to at least have some level of computational work. I wanted to do some, but one of the profs never got back to me on it, so.
I did some of my PhD. It's one of these things you just end up learning it because it's easier than trying to make someone do it for you. It seems really scary at first. It looks really hard, and it's really not. it's as soon as you get hands on how you're inputting them and stuff. I really didn't want to do it at first, and now I thoroughly enjoy doing the computation. And it's really nice when it backs up experimental data too.
I'm still in the camp of being afraid of computations and
Yeah,
technology.
Math is fun, guys. Come on.
I don't know why people hate it.
I count to 4,
It's so
maybe
easy.
6 sometimes.
The computer does it for you. You just have to press some buttons.
No, the math part is good on paper.
But yeah, certainly for our work, we definitely have a computational component. But what it's kind of come down to is we've had computational collaborators as well.
That's the other way to do it, yeah. Mm-hmm.
Someone's asking what kind of computational work you did, Claire, during your PhD.
Mine was mostly because a large part of what I ended up doing was sort of spectroscopic investigation. So it was computing vibrational frequencies or UV vis, things like that. And mostly I would start from a pre-optimized geometry from a crystal structure rather than building it from the ground up.
A lot of computational chemists actually frown against doing that because that's assuming that it's already in its ground state configuration, according to one of my inorganic profs.
Yeah, but it's also sort of one of the dumb ways to do it.
Yeah.
And for things that are fairly low computing cost and have an error associated with them anyway, like vibrational stretching frequencies, I think it's okay.
Yeah.
What do you think about the word olefin for alkenes? That's the personal question I have.
Yeah, often.
I use it sometimes.
I can't see it in a textbook, and I just.
I think it's quite historic, isn't it? It's quite classic.
It's used so much in parlance. Like, I don't know if I had to call everything an alkene. I mean, okay, so imagine like working with an international cohort. You know, everyone pronounces their vowels a little bit differently. Trying to distinguish between an alkane, an alkene, and alkyne in conversation gets a little bit cumbersome. So if we could just call it an olefin.
I had that issue with my mom, actually. I was telling her about some chemistry and confusing alkene and alkynes because of that. Because we weren't sure what language we were using.
Well, you know what they say, it takes alkynes to make the world.
This has got nothing to do with anything, but Oliver, what is that bottle on your shelf?
Oh, it's some 37% hydrochloric acid, I think.
What is it?
It's human hydrochloric acid, but it's empty though.
Oh, okay. Sorry, I've just been looking at it. I'm too easily distracted.
Analytical grade hydrochloric acid.
Looks
Stuff
nice.
you have around in your room.
Yeah.
I used to have some ferrocene there, but I don't have it anymore.
Would have been thematic.
I put some books up, but actually, do you guys have any textbooks to recommend to people on the field?
Absolutely. Crabtree's Organometallics textbook is the single friendliest. Yes, there we go. I have the green one, but that's the new edition. It's the friendliest place to get started in organometallic chemistry.
And there's this one, too.
Which one is that?
Spessard and Miessler.
Miessler and Tar?
I had Miessler and Tar in my inorganic chemistry course.
Yeah, that's the one that I have.
Astruc, but it's a French author.
Which
you, Claire?
I have one.
No.
Sorry.
No.
one I really enjoy is by Yves Jean. It's called Molecular Orbitals in Organometallic Complexes.
Oh wait, I might have that.
It's a thin book. But it's a nice deep.
Orbitals in transition metal complexes, but I don't have the organometallic one.
That's probably the one. Is it purple or?
Yeah, it is. Wait.
Yeah, that's the one. Okay.
Don't know where I put it though.
But I mean, so there's a question here: any advice for a 16-year-old getting into chem? I think with organometallic, the best way is to really go through university, because you do the first year of university of like really not basic stuff, but the base knowledge that you need to then apply to organometallics.
And a lot of it's dangerous, just flat out dangerous to do at home. So
I'm not sure we're
free
doing it at home.
Yeah, but you usually have to do organometallics at a university level.
Oh, I've done air-free chemistry at home, but
okay, yes, Mr. Person who buys from Sigma Alder, who gets more funding than you got more funding in a month than my entire lab got in a semester.
Yeah, but that's just.
Oh, but did you use balloons? How did you do it?
I've got a schlenk line.
You have a schlenk line at your house. That's the dream.
I did some. I mostly did titanium chemistry though. Like titanium 2 and titanium 3 cyclopentanediol complexes mostly.
Nice.
Someone's asking how you get the funding.
I've usually seen it home chemistry, but it was fun.
So I could tell you, I was also a home chemist once upon a time, probably about when I was 16 or so, getting into chemistry. And I'm over 30 now, so sorry, I'm the old person in the room. But it's kind of fun, like looking back and thinking, what would I have done differently at that age? And realistically, I have to be honest, I was not accomplishing much in the garage with my experiments. Sure, it was fun to splash around with chemicals. And I know that there are people who have done much more interesting experiments than I've done. And, credit to them. If that brings them joy, I say keep doing it as long as they're being safe. But to me, the real lesson I took from garage chemistry was, becoming the chronic label reader, going to the hardware store and figuring out how I could divert every household product to some nefarious means or other. And what that does, that's a real rabbit hole. It makes you start wondering, like, why is this chemical used in this consumer product or this commercial application? It gives you some understanding of like the properties, the reactivity of these chemicals. You get an idea. You become like interested in figuring out where they come from, the processes that make them. Every chemical starts to get a little bit of a personality to you when you have so few and the pace of work is so slow. And to me, that's getting the understanding of like the global chemical supply chains, I think really helped to develop my interest in chemistry now as a more established researcher.
Yeah, I agree. I mean, Tom, you're the best at this. You're making explosives in your shed while doing a PhD in explosives.
Don't say that. Just because it's true. I mean that's true about the chronic label reading. I mean, you become really aware of it and all that's going on. And I suppose for me, the best bit about home chemistry was really being able to stay motivated to do chemistry, which is one of the hardest parts, because chemistry as a degree is pretty difficult and it gets pretty intense at points. So it's hard to stay motivated and think, this is still a subject I like. Because sometimes you have entire courses where you think, we haven't really talked about a chemical for the entire time. It's just been point charges and rate equations and like you think like
point groups.
Ideal
Those
gases.
are fun,
Oh yeah. But sometimes it's sometimes for me anyway. It was good to remember that. Yeah, there's still chemicals in chemistry, and and it's all like like not. I'm not dissing on those fields of chemistry, but it's you do it because you like it, and you see a lot of people in the chemistry degree. I don't know about you guys, but people were there and they didn't really like it at all, and you could tell. And it makes the course a lot worse if you're doing something you don't really enjoy.
Yep.
you could throw a beaker in any direction and hit a depressed grad student.
Yeah.
Yeah, I mean, I finished my finals in this winter, and then I went straight to my lab, to the home lab, because I wanted to do some chemistry. So that's nice. You keep on doing chemistry, but you do it. It makes you enjoy it more. Though I'm a horrible home chemist because I just buy stuff from Sigma and Actos, and that's it.
Hey, it's the Aldrich synthesis.
Yeah, I synthesize my precursors by ordering them and not making them. I mean, that's how I'm able to do like more serious stuff rather than spending 10 months on making, don't know, some super basic, like making ether, for example. I just buy 5 liters of ether and I'm good.
I used to buy it from starter fluid in the like an auto parts shop.
Yeah. Classic.
Yeah, I mean, there are different ways of doing home chemistry.
Claire's looking slightly concerned. I'm sorry.
I have not done any home chemistry. I'm not sure how much I approve of, but
Yeah, sorry. We're just descending into, so what do you just do it from starter fluid? Like, no, but
No, I always tell people that like the spark that lit up my eyes was tear gas that I made in my garage.
Oh God. Oh God. I have a few more.
Yeah, okay, we get it. We get it.
I'll just stick to baking and cooking.
Yeah.
There was a reason why I have a bread body pillow.
Yeah, that's kind of worrying though. Do you guys see yourself more as organic or inorganic chemists?
inorganic.
Organic. Sorry.
And what other fields did you consider when specializing?
Physical chemistry.
When I started undergrad, I was really into medicinal chemistry and natural products and total synthesis stuff. And for whatever reason, like I just couldn't stand being in an organic lab at the time. The fumes gave me headaches and stuff, so I didn't like it. So afterward, I got into like geochemistry and analytical chemistry for a while, and then eventually like environmental chemistry, kind of combining those two, getting into ecotoxicology. But then I kind of came around to realizing that organometallics and catalysis was the coolest thing in the world, and got into zygomatic catalysis, polymers, and heterogeneous catalysis, and then I don't know, got into homogeneous catalysis from there.
Wait, what the hell's geochemistry?
You've never done I did one subject in geochemistry, and it was amazing.
Really awesome.
Never encountered it before in any way.
It's
chemistry, sure. Astrochemistry, sure, but geochemistry?
Yeah, so I took a course in undergrad with a really great guy at the University of Maryland, Bill McDonough, and he was interested in studying meteorites and the composition of rocky meteorites. And awesome. He would bring to bear all kinds of really cool techniques. I mean, the one that I kind of learned the most about was inductively coupled plasma mass spectrometry, and then all the different sampling methods with that, like laser ablation and surface analysis. It's just you get it looks like the Death Star. You shoot a laser at a meteorite, and then you get to shoot the thing through a plasma. How cool is that?
Yeah, geochemistry is a cool field. And you can get a pretty nice job out of the degree as well. Yeah, so I mean, if you like environmental stuff and you like some chemistry, some geology, geochem's a very, very cool field to get into at the moment.
I mean, you get to work with crystals, and crystals are cool.
Yeah, that's it.
And annoying. Any of you done photoredox catalysis?
No.
No. The lab, 2 labs away from me, does that, and it looks really cool.
Well, down the road in that direction is another university that's kind of the center of photoredox catalysis. But toward like commodity scale applications, photochemistry is not ideal. In fact, my PI, when he started this lab, was interested in, his early work was on using UV light and organometallics to do some really cool carbon-carbon bond forging reactions. For example, accessing superlinear alkyl benzenes from benzene and olefins, which is still kind of a very desirable reaction. But if you do it with like UV light, at least, then you're talking about an exorbitant price for a commodity detergent.
Yeah, that's true.
But that's different from photoredox and visible light. The trouble with visible light, though, is again, if you have to look at, if you've ever seen a refinery and have a sense of how large even 1,000 gallons is, much less 50,000 gallons. Visible light just doesn't have the penetration to reach into those reactors and assure efficient energy transfer or whatever to initiate these catalytic cycles. So a lot of the visible light work today is still kind of it goes hand in hand with reactor design. It goes hand in hand with flow chemistry, wrapping tubes around light sources, or using peristaltic pumps to keep a reaction in flow.
Yeah, they're usually like tiny tubes. Yeah.
Yeah.
The university does a ton of photochemistry.
But I don't think that's going to be a permanent situation either. I'm not going to write photochemistry, visible light photo redox off. I'll just say it's not necessarily applicable to what I do. I think there's been some interesting work using, for example, lasers or what's it called, photon upgrading, combining two photons of lower wavelength and higher wavelength. Upconversion. There we go. And that those, with continuing research in the area, I think we'll see a lot of promise from that.
Yeah, that's kind of my field.
What's the most dangerous situation you're in?
Yeah, actually, before we ask that, I'm going to say we're running pretty long. It's been really interesting, of course, and so I guess we'll do the final question of, no shame, no nothing. What's the, have you broken something? What's the worst sort of accident that's happened? Has there been something really dramatic in the lab? Because I know people like watching me break things on my videos. I'm not sure they like watching it, but
I can start then. My project needed a lot of air-free filtrations, and the filters for those are about $250 a piece. I had one clean. None of the others ones were clean or dry. And then I was putting on a 1420 adapter because I only had a 1420 to 2440 adapter because I had a large volume solvent. It slips out of my glove, like the oven glove, directly onto the filter, shattering it completely. Out a day of work and one of our 4 filters that each cost $250. It was just horrible, kill me. I also broke a Strauss flask, but that one's not as terrible.
What's a Strauss flask?
It's a large 500 milliliter round bottom flask with, instead of having the main neck just straight through, it blocks it off, has a sidearm that goes in, so you can have a stopcock that you can use to attach onto a Schlenk line, keep vacuum or nitrogen on it.
Okay, interesting.
The most dangerous situation you were in, Andrew?
Probably working with KFIP because it's very, very nucleophilic and will attack water and start catching fire.
Yeah, because all of you work under inert gas the whole time, right? Yeah, because
my PI really actually KH. I've worked with KH though, and that was a bitch.
Oh, potassium hydride.
Yeah,
because that catches fire very easily, right? On kind of with air. For context,
water. It's in a mineral oil dispersion, so it's fine. But if you chuck it in water, it just starts going up in flames.
Is it packaged like lithium aluminum hydride? Because they sell it in cans.
Mine wasn't. It was just in a jar, plastic jar. About 30 years old. It's fine. It's fine.
If you really sit down with me at a conference, I can tell you all sorts of fun stories. And I'm afraid of putting some things on the record here.
Sorry, you don't want to throw anyone under the bus here.
No, my PI is going to watch this later, so I can't let him know what goes. But probably not so much in this lab, but my prior job with WR Grace, I was visiting their Organometallics catalyst plant where they manufacture zygomatic catalysts on a 1,000-gallon scale or so. This is my first visit to this particular plant. And lo and behold, they made us wear flame-proof lab coats and helmets. And they said, you're going to need these. What can really go wrong?
You're going to need these.
Well, you might need these. Yeah. And so we get to their raw material storage farm, basically. It's like this bay where they hold the 1,200-gallon tanks of things like titanium tetrachloride or butyl ethyl magnesium. Think like 2 Ford F-250 trucks stacked one on top of the other. So we're kind of looking at it, just admiring, going, ooh, ah. And he's telling us about like the automatic flame suppression system that uses that aircraft foam or whatever. And then my supervisor, she goes one of these numbers. She goes, "Fire!" and just runs. All right. So then everyone else kind of gathers around and goes like, "Hey, to the engineer, you got a fire coming out of this butyl ethyl magnesium tank." And meanwhile, home chemist, my fight or flight reflex is completely fried. So I was kind of sitting there staring at it until they said, "Tariq, you need to get away from that tank." But and yeah, he put it out with a little fire extinguisher. It was just like a leak coming out of the top manhole. So.
Wow. Yeah, they must live on the edge every day in those sort of plants.
Yeah.
What about you, Claire?
Nothing like that. Yeah, so a lot of the stuff I worked with was like a bit paraphoric. So I've worked in quite a few labs, so I feel like I can say stuff as long as I don't say which lab it was in. But I have had small fume hood fires. So, for instance, we don't use glass. When we're doing filtrations, we don't do, for instance, inverse filtrations. We would use cannula filters to have just a little bit of filter paper and a glass filter paper as well on the end of them. But if you make cobalt nanoparticles, for instance, those are paraphoric, especially if they touch tissues, things like that. So I used to have a waste bag in my fume hood. So I just cut the filter off. Didn't realize my reaction had decomposed. Went round to the sink to do some washing up, and then I could just smell smoke and around, waste bags on fire. It was fine, just a bit of liquid nitrogen, that's fine.
Oh, God.
It was on a Friday afternoon, though, that's the problem. I had a train to go and catch. So I was like, oh, God, I don't have time to go to fix this because I have to go and get a train. So just leave it.
Yeah. My lab has just banned all like maintenance work and anything remotely risky on like Friday afternoon, because it just goes like you do anything on Friday afternoon, you're feeling good, and then it goes wrong and everyone wants to leave.
Friday
things go
afternoon's
worse.
the time for doing weird experiments, though.
Or Saturday or Sunday when no one's around for stuff with tiles.
Oh, well, the tiles, I think they stay in the air, though.
That's what the purge button on the fume hoods is for.
Just put it into the atmosphere.
Nature's bin.
Nature's bin.
I mean, we're usually working on trace amounts, so as long as we're not like dumping solvents down the drain to kill the fish, then we're usually fine.
Usually. Yeah.
Reassuring.
I did all my smelly chemistry late at night. Was I doing a dithiolane protection or something? It smelled like nachos to me. It smelled like food. But
that
everyone else
sounds pretty good.
I thought it was all right at low concentration. Everyone else said it smelled just so objectionable. They were so offended by it. So I'd have to bleach out the rotovap and disassemble it before I left for the day.
How does COD smell for you guys?
Awful.
It smells like oil paint and rotten fish.
Like offensive rubber or something?
What's the question?
Cyclooctadiene.
COD.
Oh, COD, yeah.
Oh, yeah. No, I can't stand it.
It stinks. It's so bad.
Yeah.
I mean, it's great, but it's horrible. And I used to paint quite a lot, and it's like oil paints, but like rotten and mixed with squid.
In the chat, there's always, people always turn up and it's like start talking about how bad things smell, and then someone's like, "Well, I work with organoselenium compounds," and you're like, "Okay, you win."
Did that once.
Really?
Well, it was. So selenium dioxide is one of my favorite oxidants. It's a really amazing little reagent, and catalyst in some cases as well. But I talked a little bit about like electron-proton transport mediators. So long story short, I was trying to use selenium dioxide for an electron-proton transport mediator. And, at the end of the catalytic run, there's some organoselenium compounds in there. Just to see how bad it really could be, it kind of wafted. It smells like bad cheese mixed with a foot after running 7 miles in the summer in leather shoes.
Oh,
Sounds horrendous. What about tellurium? No one ever works with tellurium. It's probably too bad.
Yeah. Anyway, okay. Well, I feel like we can talk courageous. This obviously chat has heaps of questions, but I think it's time to finish up. And so I thank you very much. And if I will say, if you're in the chat or you're watching this and you're interested in these people's researches, they do have Twitter, and of course they publications out. It's always nice to have your publications read and cited. So everyone in chat, cite these publications. Or you get banned from a research site if you suddenly got 1,000 citations overnight or something. Maybe.
I'm going to post the link for mine right now.
The links will be in the description for YouTube.
We'll link everything.
Yeah.
Tom will on my channel.
And
Thanks so much, guys.
All right. Thank you so much for organizing, Tom and Oliver. This is really great.
All right.
Nice to meet you, Claire and Andrew.
Yeah,
you
you
too.
You too.
All right.
And I'm glad it worked out so well for the first one. Hopefully,
so far.
Hopefully, we can continue.
Yeah.
Do more of these, and we maybe will have you back on in a few episodes again.
Yeah. No, thanks everyone for tuning in. Yes. Okay. Goodbye to each. It's time to go. It's just me and you now. It's just an ASMR. No, this is immature. All right. How do I stop this? I'm so bad at this.